name David. Taught us the singularity structure of gravity. Okay, thank you very much, organizers, for invitation and for a nice conference. And I will talk about some recent work, and the work is in progress with Enrico Herrmann, who's in the audience. There is also a related work by Paul Heslop and Arthur Lipstein. So first, before talking about physics, I would like to announce some meetings. One of them will be in Mainz in February 2017. And the other will be in Davis, and it's an inauguration conference of our new Center for Quantum Mathematics and Physics. People who are interested, please apply. And now the goal of the talk is to take some mathematical structures that we saw in the planar N=4 super Yang-Mills and try to see if they can be extended or modified, first in the case of non-planar amplitudes in N=4 and then in N=8 supergravity. And the questions I would like to address here is first, in general, do the non-planar integrants have some special properties? Can we think about them in the same way as in case of planar integrants, which are uniquely defined, and the story I will review in a moment shows that these are very nice objects to study. And then specifically N=8 supergravity, take these integrants and to show or to study the singularity structure and also to see how the IR and UP behavior are encoded. Now, as Alice mentioned, it's a good method for studying amplitudes to study their singularity structures. And we can either study the singularity structure of final amplitudes, where we don't have any loop momenta, but we have a space of complicated functions, and there has been a lot of progress in the last few years in thinking, in studying these functions. There was a talk by Mark Spradlin, and there will be also a talk by Lance Dixon about another approach. But in this talk, I will look at the loop integrand, which is the function which is supposed to be integrated. The function has loop momenta inside, but it's just a rational function, and it has a simple singularity structure, or the unitarity is a very powerful statement about the poles of the loop integrand and the residues, which are either on the poles, the loop integrand factorizes into the product of two pieces, or it goes to the forward limit. And there is also more famous statement of the unitarity cuts when two of the propagators go on shell. Okay. Now, the generalized unitarity is the procedure where we use these singularity equations and iteratively cut more and more propagators unless we actually factorize the loop integrand into the products of trees. If we cut everything we can, then this corresponds to maximal cuts. But even if we go farther from maximal cuts and we factorize even the tree-level amplitude as the product of 3-point amplitudes, we land on on-shell diagrams. So the on-shell diagrams are pictures looking like that, and they are defined as the product of tree-level of 3-point amplitudes, which are fixed in the massless quantum field theory to any loop order. And these pictures are either products of tree-level and 3-point amplitudes, or they can be also thought as the cuts of loop integrands. So the first one is the quadrupole cut of one loop 4-point integrand. The other one is the octacut of loop 5-point integrand, and so on. These on-shell diagrams exist in all theories, but there are some special properties in planar N=4 super Yang-Mills, and also non-planar in N=8 supergravity. But in planar N=4, the nice thing about these objects is that they not only provide us with the cuts of loop integrands, but they can be also used to construct the loop integrands directly via the recursion relations. And this is an example of the 4.1 loop amplitude in planar N=4 super Yang-Mills, which can be represented as the one loop box integral off-shell with off-shell propagators, but at the same time it can be represented as 5-loop on-shell diagram. So that's the picture on the left, where everything in the picture is on-shell. So there are no off-shell propagators. All the lines, both external and internal, are on-shell. And as you can count, there are 5 loops inside. So that stands for the 20 degrees of freedom. But there are only 16 propagators, so 16 on-shell conditions, leaving 4 unfixed parameters, giving rise to the 4 degrees of freedom in the off-shell loop momentum. Now, there is a connection between these diagrams, defined as product of 3-point amplitudes, and the Grassmannian. Now, the connection has a very simple motivation, because when we use the standard momenta, the momentum conservation is a linear condition, but when we use the spinor helicity variables, we make the on-shell conditions manifest, but the problem is that the momentum conservation becomes a quadratic condition in lambda lambda tilde, and it's a natural question if we can linearize these conditions as separate conditions for lambda and separate conditions for lambda tilde. And this delta function, the momentum conservative delta function as a quadratic condition, can be actually factorized into linear conditions in lambda lambda tilde, and the C is the matrix of coefficients in these linear equations. And this matrix of coefficients is defined modulo GLK transformation, which is a choice of the basis elements, and that gives rise to the Grassmannian, as the Grassmannian matrix. Now, we can build from each on-shell diagram such a matrix using some procedure defining the variables associated with faces, face variables, or edges, edge variables, and there is a procedure how to take a diagram and construct this C matrix, which linearizes the momentum conservation. Now, these parameters are in generally complex, but there is a very interesting connection to mathematics in case of planar diagrams. If we restrict ourselves to the real variables, we say that these variables in the C matrix which linearizes momentum conservation are real and positive, then the minors of this matrix are positive, and then there is a connection to positive Grassmannian. And there is interesting research area in mathematics, in algebraic geometry and combinatorics, which governs the properties of this space. And it's also a very useful way how to use the recursion relations using on-shell diagrams and calculate amplitudes. Because, and the reason why it's useful is that the same diagram, which at the moment, from one point of view, was a product of 3-point amplitudes, from the other point of view, it gave us this linearized momentum conservation, can be actually calculated using parameters of the C matrix using this logarithmic differential form. So it's d alpha over alpha for all parameters of the C matrix, and the only dependence on external kinematics is in these delta functions, which are these linearized delta functions. And in addition to the lambda lambda tilde, there is also a fermionic variable eta tilde, which have the same matrix of coefficients. So this is the connection between the Grassmannian and on-shell diagrams. On one side, product of 3-point amplitudes, on the other side, the differential form in the variables of which parameterize the Grassmannian. Now, there are hidden properties in the standard way how to define the on-shell diagrams and also amplitudes in this theory via recursion relations, which are manifest in this Grassmannian representation. The first one is the dual conformal symmetry. These diagrams are individual dual conformal invariant, and also counting the superconformal part, they are Yangian invariant. In the structure of singularities, this is manifested in the absence of poles at infinity. So the cuts of the loop integrand in planar n equals 4 never localizes at L goes to infinity. So when we cut, it never happens that there is a pole where L goes to infinity. This is tightly related to the UV behavior of n equals 4 superyangular, but it's actually a much stronger statement than that. The UV behavior is just a trivial statement from this point of view, but we have, of course, we have a proof of UV finiteness also from other points of view. The other statement are the logarithmic singularities. This is how the form for the on-shell diagrams was defined. So whenever we go to the pole x goes to 0, the individual on-shell diagrams, but also the integrand for the full amplitude, behaves like dx over x, and x goes to 0, where you can think about x as a function of loop momenta and external momenta. And this is the statement about types of singularities that can happen in the cut structure, and there is a close link to the uniform transcendentality of amplitudes in planar n=4. Now, the individual on-shell diagrams have all these properties, and as I showed the formula, all the dependence on external kinematics is pushed into this delta function, and everything is formulated using these parameters of Grassmannian. But still, if we build the amplitude, we have to use recursion relations, which is a manifestation of unitarity. So here in this picture, there is still lack of some complete geometric picture. We are still using unitarity in a critical way when we build the amplitude. Now, the amplitude-hedron is the answer to the question, how if we can formulate the problem completely geometrically. It was motivated by earlier work by Andrew Hodges, who realized that for NMHE tree-level amplitudes, if we use BCFW recursion relations in momentum twistor space, we can, each individual terms, BCFW terms corresponds to volumes of tetrahedra in momentum twistor space, and the full amplitude is a volume of polyhedra. It's in the middle of the picture, and the different ways how to calculate it corresponds to different triangulations. The amplitude-hedron is the generalization of this story. There is several layers of generalization, from projective space to the Grassmannian, also encoding the fermionic degrees of freedom in bosonized momentum twistors. But there is a space which is well defined by this formula, where all the geometric complexity of this space is hidden in the C, and the loop integrand of amplitudes in planar n=4 is a logarithmic volume form on this space. It's a form with logarithmic singularities on this space. So that's the picture. Now, there is another way how to think about the same thing. There is a general statement that amplitudes are fixed by cuts, the loop integrands are fixed by cuts, and the object which satisfies all the cuts is uniquely defined to be the correct loop integrand. The amplitude-hedron provides the list of all legal cuts in the form of inequalities. So the variables kind of combine the loop momenta together with some helicity, with these bosonized momentum twistors, but let's think about it just as loop momenta. So we have some inequalities, or zk parameterized loop momenta, and we have the list of them, and we know that to all loop orders. And if the inequalities are satisfied, there is a non-zero cut, and if they are violated, the amplitude should vanish on this cut. And the inequalities have also this interpretation of defining a region in the Grassmannian, so it's kind of on top of that. But even having these inequalities is the all loop order information about the loop integrands in planar n=4. And there is a further picture which says that these inequalities are fully defined just by saying, or the existence of these inequalities can be translated to the statement that the loop integrand is defined just by saying what are the illegal cuts, where the loop integrand should vanish, and this fully defines these inequalities. So let me just show the example of these inequalities in some little slightly non-trivial example, which is a 4.2 loop amplitude. So running this amplitude-hedron machinery, we get 9 inequalities of that form. We have some variables z, z1 up to za, they parameterize 8 components in the 2 loop momenta. And we have 8 inequalities which are saying that the z's are real and positive, and then there is 1 quadratic inequality. Now going to the cuts means that we are setting some of the z's to 0, infinity, or to be equal to some other values. I remind you that the 2-loop 4-point amplitude in planar n=4 is given by these 2 double boxes. So for example, if we perform the 1-loop quadruple cut, we just cut 4 propagators, obviously the amplitude must vanish there because there is no such a cut in these 2 double boxes. And indeed, this corresponds to setting first 4 z's to 0, which is perfectly consistent with the first 8 inequalities, but the 9th inequality becomes this statement, and that is violated because all the z's are positive by definition. So this is the way how all the cuts are encoded here. But of course, furthermore, there is this geometric picture there. Now, let me talk about non-planar amplitudes. The the first problem with non-planar amplitudes is that there is no unique integrand. Because there are no dual variables, there is no cyclic ordering, so we don't even know what does it mean L. The L means different thing in individual diagrams that contribute to the amplitude. There are no momentum twisters, and we don't know about some hidden symmetries like dual conformal symmetry or IBM. Now the on-shell diagrams are still well defined, it just corresponds to cuts of the amplitude, so we can draw them, we can calculate them as the product of 3-point amplitudes. And there are some special properties in the MHV sector, and now recently also found in the NMHV sector, and Jake will talk about it more on Friday. Now, the important thing is that we can exactly use the same connection to the Grassmannian, again, take momentum conservation, linearize it, build a symmetry that all works the same, and again, there is a logarithmic form which calculates the non-planar on-shell diagram. That's all the same. The only difference is that there is no positive Grassmannian. If we take these variables to be positive, they are not positive. And there is no unique integrand, and there are no recursion relations, so at least we don't know at the moment about the way how to take these on-shell diagrams and build the loop integrand, because the loop integrand is kind of not well defined because of these problems with labels. But these on-shell diagrams are still cuts of the amplitude, so we can conjecture that whatever properties are for the on-shell diagrams, they also hold for the amplitudes. Suppose that there exists the recursion relations, but the other thing is that they are cuts of the amplitude, so somehow the cuts should also carry over some of the properties of the loop amplitudes directly. Now, these natural properties that we can conjecture out to logarithmic singularities, they are there for on-shell diagrams. The other thing is the poles at infinity. We conjecture that there are no poles at infinity, so it never happens in the cut structure that the loop momentum gets located at infinity. And also that only these homogeneous cuts, only the cuts where the integrand vanishes, are enough to specify the amplitude completely. And these three properties can be translated to, but this is a speculation, logarithmic singularities in the planar case were related to the fact that the full thing had this logarithmic volume form, that these were volumes of some regions in Grassmannian. These poles at infinity were direct consequences of dual conformal symmetry in the planar sector. And these homogeneous cuts were the content of these scattering inequalities and furthermore the amplitude integral. But at the moment we cannot check the right-hand side, but we can check the left-hand side just directly on the results in the literature. And as I said, we don't have recursion relations, so there is a conservative approach, is to take the amplitude and expand it in terms of integrals, color factors, and some coefficients A. And now we allow ourselves to fix these coefficients only by vanishing cuts. So no cuts with some non-zero function on the right-hand side. This is not accessible for us at the moment. Some diagrams are directly forbidden. For example, at 2-loop, this diagram is forbidden because there doesn't exist any way how to choose any numerator such that there are logarithmic singularities and no poles at infinity. These two properties we impose thermodynamically. And the checks we did at 4.2 loop, 3 loop, and 3 loop and 5.2 loop say that this is indeed true. So all these properties I showed before are true for the non-planar amplitude. Of course, more checks are needed because these are just 3 examples. Now, the non-planar conclusion here is that the same properties of amplitudes as we saw in the planar sector are there in the non-planar sector. We cannot formulate them as symmetries, and we don't know the geometric formulation for it. But my bet is that the main problem is the absence of these global variables. We don't have good variables in which to formulate it. But the consequences of what was consequence of these properties in planar sector are there exactly non-planar. I think that also the role of color factors we kind of ignore here. We just put the correct color factors there from the beginning is critical. And if there is a complete story, the color factors must play a crucial role as well as they play in the BCJ relation. Okay, so even without going farther in non-planar angles, we can just look what happens in gravity, and from the same perspective look at the gravity amplitude. And the starting point are gravity on-shell diagrams, because again, they are well defined. We can take 3-point gravity amplitudes and glue them together, and we can just get some data in the beginning. The simplest class of on-shell diagrams we can calculate are MHV leading singularities. So these are on-shell diagrams for MHV amplitudes, and leading singularities means that there are 4 L propagators. So these are just pure functions, rational functions of external momenta. Now, so here are some data in the Yang-Mills and in gravity. So if we just do the straight calculation of gluing together 3-point amplitudes taking the products, we get this. We take more complicated on-shell diagrams, we get this. This is some non-planar one. In gravity there is no reasonable planar sector, so we have to treat all of them at the same footing, both planar and non-planar. And based on these results, we could already make a conjecture for how the functions would look like, that there would be some square brackets in the numerator and angle brackets in the denominator. But if we calculate more, it turns out to be false. There are actually higher poles in the denominator. There are only angle brackets, but the numerator can become more complicated. However, there are some important features of these on-shell diagrams which will then carry over to also gravity integrands. And that's that the higher poles in the denominator only corresponds to poles at infinity. So if we sit on 2, 5 goes to 0, the sum of the internal loops of this diagram blows up. So the L goes to infinity in that case. This never happened in the Yang-Mills case. That was, the on-shell diagrams manifestly didn't have these poles. And there are also interesting numerator factors, which are not in the Yang-Mills case. There is never, the numerator in the Yang-Mills case doesn't have some special properties, but here it does. And the numerator factor says that in each vertex of the diagram, whenever 3 momenta are collinear, the diagram vanishes. So there are some collinearity conditions in each vertex. Now we can try to take this insight and guess and then prove what's the Grassmannian representation. So this is just a reminder what was it in the Yang-Mills case. We took the diagram, we associated variables, for example with edges, constructed the symmetrics that linearize the momentum conservation, and wrote the form on the variables of the Grassmannian, which exactly reproduce this expression. Now, this is for Yang-Mills, so n equals 4 super Yang-Mills. There is a simple generalization to Yang-Mills with any number of supersymmetries. And in gravity, it looks like that. You see that instead of single poles, there are cubic poles, and there are some deltas. These are the numerator factors. Now, analyzing this expression more closely, these higher powers of alpha corresponds to poles at infinity. So there are poles at infinity of arbitrary degree, not just single poles, but double poles, triple poles, and actually there are even higher poles, which can come from the numerator. But whenever alpha goes to 0 corresponds to some finite loop momentum, not infinite, they turn into the single poles. So at finite loop momenta, which means on cuts, there are only single poles. And the diagram also vanishes if the 3 momenta in the vertex are collinear. And there is a similar formula for n less than 8 supergravity by multiplying by some extra factor. It's exactly the same factor as in Yang-Mills. Now, there was also work by Paul Heslop and Arthur Lipstein who studied these on-shell diagrams in the context of BCFW recursion relations. In this case, there is another level of structure. In the Yang-Mills case, the sum of on-shell diagrams directly gave the 3-level amplitudes or loop integrands. But in gravity, because of dimensional full coupling, the BCFW recursion relations have an extra 1 over S factor. This comes for the BCFW sheet, there is extra 1 over S factor. So the 3-level amplitude is not a sum of on-shell diagrams, it's a sum of decorated on-shell diagrams. And in this work, they studied these decorations and found a way how to calculate and how to use on-shell diagrams to build 3-level amplitudes. Okay, so this was about on-shell diagrams. So now, what are the implications for gravity amplitudes? So again, we don't have any loop recursion, and we don't have good variables. And this is a generic non-planar problem, not just in supergravity. It's the same in non-planar Yang-Mills. But we can make conjectures for loop integrands, how they behave. Now, there are 2 statements which probe the IR region. And that's the statement about these logarithmic poles for cuts. So whenever we cut, it always There are only logarithmic singularities. We always find dx over x. We never find dx over x squared, and so on. And the other is this collinearity condition. So whenever on the cut we have free on-shell momenta in the on-shell diagram on the cut, then this cut vanishes if these momenta are collinear. So I will show an example of what it means. And there are certainly poles at infinity, as they are in the on-shell diagrams, and that corresponds to some UV properties I will comment on as well. So first, these logarithmic singularities. So as I said, if I have an integral all the amplitude and I do sequence of cuts, it never happens that we have d alpha over alpha squared. It is much more than just having simple poles, because we can have the forms with single poles, but on the cuts, the double poles and multiple poles are generated. But the conjecture is that never happens, and actually we can almost prove it using combination of two different conjectures. One is BCJ, but it's more specifically, it's the statement that we can write a Young-Mills amplitude using BCJ numerators without any poles, so that the BCJ numerators are just polynomials. So we write the Young-Mills amplitude in that way at the loop level, for n equals 4 super Young-Mills. And the other statement is that we can always write the representations when term by term in the expansion, the integrals in the n equals 4 super Young-Mills amplitudes have this logarithmic singularity, so they have these properties. So we already conjectured before for the amplitudes that the full amplitude has this property. Here there is a further statement that the individual diagrams can be arranged, the numerator can be arranged such that the double poles never show up. And this we checked in this series of examples, two-loop and three-loop examples, and it was correct. So if these two statements are correct, then the gravity amplitudes can be obtained by the double copy, take one copy of BCJ and the other copy of this D-log representation. Now the D-log representation automatically kills all possible double poles from the denominator, and the BCJ cannot spoil that because it's just a polynomial. So that would be a proof if both of the statements are correct. And by the way, again, this prohibits some of the integrals to show up in two-loop and higher loops gravity amplitudes. For example, this integral shouldn't show up in two-loop 4-point amplitude in n equals 8 supergravity, because that violates the logarithmic singularity statement. There are other arguments why this diagram didn't show up, because it doesn't show up in the amplitude, but this gives, this rule directly prohibits that. And there is an infinite class of diagram and higher loop orders that are prohibited using the same rule. Now, I would like to talk a little more about this collinearity condition. So this is basically the statement. So if we have some on-shell diagram where the gray thing is anything, any cuts, then if there are three momenta which have the lambdas proportional, they always generate, there is always the factor L1, L2, the square bracket generated in the numerator, and then oppositely for the other helicity. This is a general statement that L's can be external momenta or internal momenta. In the special case where these L's are external legs, then this just reproduces the known formula of how the amplitudes behave in the collinear limit. But this is more general because the L's can be also loop momenta. And in particular, we can do the simple example at one loop, 4-point, when we consider this double cut. So we just cut L square and L minus P1 square. And we use this parametrization of L, so we choose the solution where L is lambda 1 and some lambda L tilde. And now this prediction, or the on-shell diagram, behaves like L1, the square bracket in the numerator. And there is a direct relation between that and the IR behavior of gravity. So we know that the gravity at one loop behaves only like 1 over epsilon in dimensional regularization. And there is a cancellation of the 1 over epsilon square pieces. And we can see this cancellation directly at the level of integrand in this region. So if we take 4.1 loop amplitude and write it as 3 boxes, each of them would scale like 1 over L1. The sum of them would scale like 1. And that's the cancellation. So 1 over epsilon square pieces cancel between 3 boxes. And the same is true at the level of integrand. for this cut, the 1 over L1 piece cancels. The fact that the sum is 1 kind of violates our prediction that the same factor should be generated in the numerator, but there is a glitch, and that says that we chose some particular labels, but there is another labeling when we kind of flip the L and L minus P1. So if we sum over all labels of these three diagrams which admit this cut, we actually get the correct expression. So the symmetrization is crucial here, and the two-loop check, we did also two-loop 4-point check, and then there is a cancellation between all diagrams contributing to two-loop 4-point amplitudes in all possible labels. And only if we sum over everything, we actually get the desired behavior of the integrand. I think that this symmetrization also plays a crucial role in the pre-integrand story by J.J. Carrasco. I think this is closely related, saying that in order to see these behaviors at the level of integrand, we have to symmetrize over the labels. Okay, let me also comment on poles at infinity and the UV behavior in an equal state, because these things are intimately connected. Now, the poles at infinity are present in an equal state supergravity. They start at 3 loops. We can consider this on-shell diagram, which is a 10 cut of the 3-loop amplitude, and it's parameterized by 2 variables. I just show one of them. So, and in one of these variables, this diagram behaves like dz over z, and where L and where z linearly parameterize one of the loop momenta L. So there is a pole at z goes to infinity, which sends also L goes to infinity. So there is a pole at infinity starting at 3 loops. And there are higher poles at higher loops. At 4 loops, there is a double pole at infinity, 5 loops, triple pole, and so on. It just grows. Now, generically, these poles are located in the complex plane. So that's kind of the point of the unitarity, of the generalized unitarity, that once you start to cut propagators, the solutions for the cuts, the loop momenta are complex. So here also, so this L goes to infinity is in the complex plane, not in the real plane. And here the detailed description of the space of poles at infinity is needed to actually understand what's the relation between them and the UV behavior. Now, we know that the expected divergence in an equal state is at 7 loops. And indeed, if we consider a corresponding on-shell diagram, or a maximal cut in this case, if we just cut all propagators in this diagram, it gives an on-shell diagram, which has the pole at infinity. In this case, it actually has the higher order pole at infinity. Now, the problem in identifying if this pole at infinity causes UV divergence or not is the difference between between the real and complex kinematics. The pole at infinity are generally in complex momenta. If they show up, if they happen to be in the for real momenta, this causes the divergence. We can actually understand it at one loop, where at one loop the triangle integral has a pole at infinity in complex momenta, but the triangle is finite, where the bubble has a pole at infinity for real momenta and it's divergent. But in general, it's very hard, because it's very hard to identify if the pole at infinity in a given on-shell diagram is the solutions for the momenta are real or complex, or if it admits some real corner or not. But that's the main question to find out that. Now, there is an evidence that these poles at infinity indeed show up only at higher cuts, because if we consider the lower cuts, like this one, there are no poles at infinity in an equal state supergravity, and that was actually the similar analysis in a little different language was already done 10 years ago, studying this type of cuts. Now, in these cuts, there are no poles at infinity for the amplitude, but if we take the diagrams that contribute to the amplitude, they individually would have poles at infinity, so there is a cancellation between these diagrams. Now, this is not a proof that anything nice happens for the amplitude. It just means that the poles at infinity are not here or there, but there is a cancellation between different diagrams that contribute here. Okay. But if we now start to cut farther, so these blocks, let's say, are the 3-level amplitudes. If we start cut farther and factorize them, the pole at infinity shows up, and when it hits the maximal cut, which defines integral contributing them, it's definitely there. Yeah, so there is somewhere the point between starting with this lower cut where there is no pole at infinity going to the maximal cut where there is certainly pole at infinity. At some point it kicks in. The question is, where does it happen? Does it happen for real? Does it happen for real or complex kinematics, and does it cause the divergence or not? This is not understood. Now, if we think from the other side about the UV divergences, and we expand the amplitude in terms of integrals, there has been seen in different cases that for theories with lower supersymmetry, there are these enhanced cancellations. The UV divergence cancels between different integrals, and presumably this corresponds to cancelling poles at infinity between these integrals in the real kinematics. We know that this cancellation happens for complex kinematics, but this is not directly linked to the UV behavior. But if it happens for real kinematics, that would be the example of such cancellation. And of course, studying the lower supersymmetric cases allows us to go to the lower loops and not to go to 7 loops or so high. The encouraging aspect of this story is that we saw these cancellations in this IR region. So at this one loop examples, I showed you that cancelling cuts between different amplitudes, between different diagrams, cancel this 1 over epsilon square piece in the IR. So cancellation between diagrams is possible in IR. So presumably it might be also possible in UV. Now, for me, the crucial question here is, which is related to the UV question, but it's not necessarily the same, is that what is special about the loop integrands in n equals 8 supergravity? And I think, as the question for n equals 4 super Yang-Mills was this singularity structure, logarithmic singularities, and also this set of inequalities which gave rise to the amplitude-hedron, there was some rigidity here. The object was uniquely defined by these properties. In n equals 8 supergravity, I think that it's the structure of poles at infinity, which are absent in n equals 4, which must define the object. There must be some rigid structure, and presumably it will be linked to the UV behavior. Now, as many people say, and I think it's true, the key to understand gravity is already hidden in tree-level amplitudes. And there are certain properties of cuts which can be understood as the 1 over z square behavior in the BCFW shifts and so on. So I think these are all very important things. But from the point of view of amplitude-hedron and this geometric construction, everything started, as I showed before, studying NMHV tree-level amplitudes in Yang-Mills case. And there was this picture of Andrew Hodges polytopes and so on. So now the natural thing, the natural thing is to look at gravity for the same structures. I just want to say it's a different than BCJ because these polytopes don't really have the Yang-Mills representation, the BCJ Yang-Mills representation don't have this interpretation of polytopes. This is a different local representation that has this interpretation. And we can look at gravity if something like that is true. So is there any polytop type interpretation? The big picture is that if it is, maybe you can write these scattering inequalities at both tree-level and loop level, and that would say where the poles at infinity are located. Are they located in the real plane or complex plane? This is exactly what these inequalities and the amplitude-hedron in plane n equals 4 told us, where exactly all the singularities are located. But here, everything starts with the tree level, so understanding the tree level in the simplest possible setup, which is the NMHV tree amplitudes. There are beautiful formula by Andrew Hodges for MHV tree amplitudes in n equals 8 supergravity, but this is kind of analog of the Park-Taylor factor. Everything starts in NMHV to see tool conformal symmetry in Yang-Mills and the farther structures. So NMHV tree amplitudes in gravity is also the starting point. And the encouraging preliminary results is that if we translate this picture, which is in momentum vector space, to momentum space and study the momentum space expressions, they look suspiciously similar in both Yang-Mills and gravity. And we have now further evidence for that. So it's possible that there is a similar story for both Yang-Mills and gravity in what the tree-level amplitudes are. And this would, the fact that the In Yang-Mills case, it looks like this simple formula is actually tightly connected to the conformal symmetry. We don't know about any such symmetry in gravity, but you see that in this simple case, when this one expression corresponds to volume of one of the tetrahedra, in the Yang-Mills case, in the gravity case, it shouldn't be anything. It doesn't have to be anything special, but the expressions are very suggestive that there is some hidden structure in the three-level gravity amplitude. Okay. So this is the conclusion. So I showed the Grassmannian formula for gravity on-shell diagrams, which gave rise to some conjectures about IR properties of gravity integrants, which we checked for a number of examples, and that seems to be true. The poles at infinity must be explored in the future, and that is the key to understanding the UV behavior from the point of view of integrant. And there are also some first signs of some geometric structure in E-level amplitudes, which eventually might lead to some geometric interpretation.
Questions?
Say that the key to understand gravity is
Wait.
three levels. Okay, I have heard that many times.
Yeah.
And I would like to, let's say, to hear from you what's the real meaning of that statement. What's
well,
the content of that?
Well, the moment we don't see it. Well, the statement is there are some new structures at loops, they should be already there at the tree level, and I'm not aware of any hidden symmetries or special properties of tree level amplitudes in gravity. Well, there are some particular statements is that some of these higher loop cancellations can be actually understood as consequences of, let's say, largely behavior of BCFW shifted tree level amplitudes, because in the end, once we cut loops, we get trees. So if we want to understand what these cuts are, it's hidden in the trees already. The other statement is here directly related to this geometric picture, because in amplitude-hedron, the trees and loops are unified. They are all in the same language, and it starts with NMHV trees. So if we can put it in the same language as loops, it should be already there at the trees. And these are easier to analyze. But from the point of view of loop amplitudes, these poles at infinity, these on-shell diagrams are just products of trees. So the properties of the tree amplitudes carry over to the cuts of loops. And this statement about if the things are real or complex, which I think is crucial to understanding if there are UV divergences or not, they should be encoded in the properties of trees, how they behave, how they behave for real or complex kinematics or so on. But it's a pure speculation.
Henrik.
Have you thought about looking at N=4 supergravity amplitudes? Because you can recycle N=4 integrals,
right.
And you also have UV divergences study at one loop.
Yes, so we look at it, so it's an ongoing work with Zvi, Enrico, Julio, and JJ Stankovic. Looking at the simplest case is the one loop 4-point amplitude N=4 supergravity when there is a cancellation and between different pieces, and the final answer is UV finite. So it seems to be that, well, there are certainly poles at infinity. The question is exactly how they link to the, where they are located. So there are bubble integrals in the expansion, but it seems that there is cancellation between bubbles, which gives rise to the finite expression. So what I said, this relation between the poles at infinity in real corresponds to divergent, and in complex it doesn't. This also omits one extremely important point, that there can be total derivatives which have poles at infinity in the real kinematics, but still after integration they get zero. They give zero. So this is another level of structure which I don't know. At the moment I don't know how to what to say about it. But there is another approach. Instead of looking at all cuts, modulo total derivatives to understand what total derivatives, what type of cuts and singularities do they match. Yeah, because it's possible there is a pole at infinity in the real momenta in the total derivative which eventually integrates to 0. So this is an extra layer, so if it happens to be the case, it's much more complicated problem than I just said. Yeah. Because then you have to understand total derivatives to all loop orders, which cuts do they match in the amplitude, and then the question is, can you take the cuts which have poles at infinity in real kinematics, push them into total derivatives, and the other ones which don't have would be the ones which are not total derivatives, and that would be to the UV finite answer.
Happens to be, I'll say something about that.
Did everyone hear that?
Just wait for my talk.
So the message is to wait till it's speech time.
Yeah.
You can't leave before the end of the conference.
Yeah, it's the last talk.
Any more questions? If not, let's thank Yaroslav. And also thank all the speakers of the afternoon sessions.